Good morning. My name is Sabine Süsstrunk, and I lead the Image and Visual Representation Laboratory, IVRL, in the School of Computer and Communication Sciences at EPFL in Lausanne, Switzerland. It is a real pleasure to give a keynote about some of our research, even though just online. I really would have liked to see all of you in Dublin, and I do thank the organizers for inviting me. So the topic of my talk is Opponency Revisited. I will primarily talk about opponency and its related terms of contrast, decorrelation, or distanglement in color images, concepts that have played a very important role in our research. Actually, I won't really mention much about political opponency. Well, you'll see, a little bit. So first of all, let me get started with a short introduction of my lab. So the IVRL, the Images and Visual Representation Laboratory, performs research that is primarily focused on the capture, analysis, and reproduction of colored images and videos. Aiming to improve everyone's photographic experience, we develop algorithms and systems that help us understand, process, measure, and visualize images and videos. So why concentrate on photography, as opposed to, let's say, medical images or remote sensing? Well, first of all, the majority of all images are photographs. Think about all the smartphones out there with its many cameras, the cameras you have on your display. It really is, photography is probably the source of the most images in the world. Well, one can argue about that. But, you know, what you can really probably not argue about it, first of all, there's nothing that people do not take pictures of. As such, it's very difficult to assume prior information when one deals with photography. And then second, it is actually a very challenging research topic because quality, with regards to photography, is in the eye of the beholder. Actually, not just the eye, but the whole brain of the beholders, as models of the eye cannot predict image quality. And third, well, that has just to do with me, because I always loved photography, and I still have not tired of the field. So let me get started with a small exercise. So, which all of you probably are very familiar with. So if I'm asking you what color is the code triplet 25500, majority of you will just say red. And that is correct. So if I communicate to my device driver, the digital triplet 25500, it will activate the red LEDs in your display. That's what you're now seeing on the screen. But what now happens? Which red? If I now insert the yellow bars between the red rectangles, can you see that the color seems to change? Or even more strongly, if I insert now also the blue bars, we're now seeing a totally different red, depending if the rectangle is surrounded with yellow, respectively blue, on the top and bottom, or on the left and the right. This visual experiment, by the way, made famous by Stephen Chabell of the University of Chicago, well illustrates that color is a percept. While it depends on physics, of course, i.e. the light emitted by your screen at this point in time, it is also processed by the human vision system, and that in a highly nonlinear fashion that we still do not fully understand. So let's go back to physics. As we are all well aware, we credit Isaac Newton with the first published color theory, at least in the Western Hemisphere. In 1666, Newton observed that the spectrum of colors exciting a prism is oblong, even when the light ray entering the prism is circular. In other words, the prism refracts different colors by different angles. This led him to conclude that color is a property intrinsic to light, a point which has been debated by none other than Johann Wolfgang von Goethe, who you might remember from your German class if you ever took German. Johann Wolfgang von Goethe is a very famous German poet and writer. What's probably less well known is that Goethe also actually dealt with color perception. He proposed a color wheel to explain how colors relate to each other. There are neighboring colors and opposing colors. He included aesthetic qualities: beautiful, so that's the purple or magenta in this illustration; noble, which is red; good, which is yellow; useful, which is green; mean is blue; and unnecessary is your dark purple. The overarching quadrants are reason, understanding, sensuality, and fantasy. So in his theory of colors, published in 1810, the original German title is Zur Farbenlehre, Goethe describes his views on the nature of colors and how these are perceived by humans. He wrote, quote, "Along with the rest of the world, I was convinced that all the colors are contained in the light. No one had ever told me anything different." Slightly passive-aggressive, right? "And I had never found the least cause to doubt it because I had no further interest in the subject." But how I was astonished as I looked at the white wall through the prism that it stayed white, that only where it came upon some darkened area, it showed some color. It didn't take long before I knew there was something significant about color to be brought forth, and I spoke through an instinct out loud that the Newtonian teaching were false. End quote. And thank you, Wikipedia, for the translation. And I just mentioned slightly passive-aggressive, wouldn't you say? Might remind us of some current researchers that cannot seem to agree on the scientific truth. Well, to take the punchline ahead, it turned out with time, of course, that both are right. So how do these two different color theories relate? As you all know, visible light is part of the electromagnetic spectrum, ranging from about 400 to 700 nanometers. That's the wavelength interval where the cones, these are the spectrally selective photosensitive elements of the human eye, exhibit sensitivity. In other words, it is the range our visual system is sensitive to. Now, if you separate the spectrum into individual parts, say from 400 to 500 nanometer, we perceive that radiation as mostly bluish. From 500 to 600 nanometer as mostly greenish, then yellow, then red. The combination of all wavelengths at more or less equal power gives us white. We exploit that in imaging in the form of color encodings, where each color image file has, at each spatial location, 3 code values assigned: one for the red channel, i.e. how much red is at that location, one for the green channel, and one for the blue channel. An additive combination of those values gives us then the color at the pixel location. Given an 8-bit per channel encoding strategy we mostly use, that results in 16.7 million different colors that we can represent. sRGB is the most common color encoding, corresponding to your camera's photo file output. XYZ is an encoding based on color matching functions of the human eye, and LMS represents a cone space. But all 3 of these color spaces actually use these loosely short, medium, and long wavelengths encodings. However, in parallel, the idea of opponent colors was also pursued. Whereas Goethe argued with Newton, Hering was the one who challenged the young Helmholtz theory of trichromatic color. Hering's representation, and subsequently Mansell's and many others, of how colors relate to each other was much closer to Goethe's color wheel than Newton's rainbow. Their observation was that certain colors just do not mix. They're opposed to each other. Take the example of red and green. Have you ever heard anyone refer to a greenish red color or a reddish green color? It just doesn't exist. However, what does exist is a yellowish red, which we call orange. The same thing can be said about yellow and blue. As such, red and green and yellow and blue are opponent colors. However, it took until the middle of the last century until researchers investigating retinal processing in the eye actually came up with a physiological explanation of why the two color theories are both correct. Besides the cones, drawn here as dome-like structures at the top of the illustration, we have additional cell layers in the retina that highly non-linearly process the input signals before passing them to the brain. So while the young Helmholtz trichromatic color vision, and thus Newton's viewpoint, is certainly correct on the level of the cones, what is passed on to the ganglion cells that carry visual information into the brain is a comparison of the signal captured by the cones compared to the signals captured by neighboring cones. This concept is called receptive fields, and they explain color opponency. It was found that we have several types of receptive fields: spectrally non-selective ones, which distinguish between black and white, and spectrally selective ones that distinguish between red and green and yellow and blue. So it is the contrast between these colors that is communicated to the brain, not their absolute values. And then it took another few years, until the 1980s, when finally Buchsbaum and Gottschalk mathematically related the two color theories. They showed that principal component analysis of the sensitivity functions of the L, M, and S cones results in an achromatic plus two opponent chromatic channels, red-green and blue-yellow. This decomposition is due to the symmetry and positiveness of the covariance matrix, as the L and M and S sensitivity functions are always positive. These channels do correspond to the measured receptive field properties of ganglion cells. This also shows that for the case of color, a decorrelation process is a possible explanation of the retinal function. Now remember that decorrelation is a way to remove redundancy. From information theory, we know that efficient information transmission can be defined mathematically in terms of minimizing the channel capacity required to transmit the information. We have approximately 2 orders of magnitude more photosensitive cells that capture light, so meaning the rods and the cones, than cells that transport the captured signal to the visual cortex. So this actually makes perfect sense. But again, took a few decades, i.e. centuries, to actually bring the two color theories mathematically together. Now, in color imaging, there are many color encodings based on the opponent color principle and many ways to transform from additive color RGB to opponent color. One of the most famous is YCRCB, which was first used in television encoding and now in image and video compression. For the sake of our research that I will present next, I want to introduce CIELAB, which you might not be that familiar with. It was developed by the color standards organization CIE, Commission Internationale de l'Éclairage, based on a psychophysical experiment by McAdam on just noticeable differences, J and D, of colors. I'll spare you the details of the experiment. The CIELAB color space was developed to make these J and Ds as uniform as possible over the whole color space, so that in this representation, perceptual color differences can be calculated as Euclidean distances in space. The axes of the space are as follows. Vertical or z-axis is the white-black and represents the lightness L. The x-axis is the red-green axis, and the b-axis is the yellow-blue axis. As such, the perceptual color difference delta E can be calculated as the Euclidean distance in that color space, as I just mentioned before. Equal delta E implies equally perceived color differences. And a difference of 1 delta E is considered a good approximation of a just noticeable difference, a J and D, in some simultaneous matching. It's not perfectly correct, but for the sake of many imaging application, it's a good approximation. So let me show you where we have used this opponent color, this decorrelation concepts in some of our research. So one of the very famous examples is in image and video compression, which I will not talk about. Instead, I will give you some other examples where we successfully applied these concepts. And in this case, I mean my colleagues and myself in the lab. So the first one is salient region detection, which is done by R.K. Achanta, Sheila Hemami, Francesca Estrada, and was published quite a few years ago. So what are salient regions? Salient regions are regions in the image that stand out or are visually conspicuous with respect to the background. So there is task-independent saliency, which is a low-level vision concept and guides human visual attention. I think, the first thing you saw on this image was the red pin, because it's different from the others. And that will be the same for a blue ball within yellow balls, and anything that basically introduces some kind of contrast. However, there's also task-specific saliency, which occurs when we do something specific. So task-independent, you would probably have seen the horse and the rider in this image. But I'm now giving you a specific task. Count the number of faces in the image, and you will see that they pop up. Well, I don't know how far you've gotten, but the currently 22 faces have been found in this image. You can go to that URL and do it yourself. The quality might even be better than on this video, but you can see more or less 22 faces. Now, I'm not going to talk about task-specific saliency here. I'm actually talking here about more or less low-level vision saliency, things that stand out. So a salient region detector gives you a map that indicates where the salient object in a scene are. Again, the method is for low-level saliency. So on the top, you see the images, and the bottom, you see a corresponding saliency map. So what should a good detector do? Well, it should, of course, emphasize the largest salient object in an image. And it should uniformly highlight whole salient regions. And it also should establish well-defined boundaries of salient object. It should disregard high frequencies arising from texture, noise, and blocking artifacts. And it should, of course, be efficient. So when we looked at this, we were actually kind of inspired by the receptive field, or its, if you will, signal processing equivalent of using something of a difference of Gaussians. And the idea is difference of Gaussian filtering is a proven and true way in image processing to find edges in an image. So we started from there. So saliency is defined as the absolute difference of the center Gaussian to the surround Gaussian. But the question, of course, is what is the center Gaussian and the surround Gaussian? So which Gaussian filter should we choose? Well, we could just try. We varied the sigmas of the center and the sigmas of the surround. So increasing surround sigmas on your x-axis and increasing center sigmas on your y-axis. Now, if you keep in mind the criteria I just mentioned, well, the best output that fulfills them is at the bottom right. In other words, a very small sigma for the center and a very large sigma for the surround. So how do we then calculate this? Well, we take an image. We basically first calculate the image average, which is similar to convolve the whole image with a Gaussian filter of infinite sigma. Then we actually do apply a little bit of a Gaussian blur to remove the noise. Then at each pixel location, we extract the CIELAB values and calculate our saliency map or our saliency indicator as nothing else than the absolute difference between the individual pixel CIELAB value and the mean CIELAB value of the picture, which in turn is nothing else than the delta E value, i.e. the perceptual difference value we defined before. So saliency is measured as a perceptual difference of a given pixel to the mean of the whole image. So what can we do with this? Well, let me just show you a few examples. Here is a sample segmentation results. As you can see, it basically works perfectly well, except on the fourth row with the little pins. As you can see, the blue pin, who is too close to actually the background, is not selected. It is a simple method, and of course, it will also fail. We've also used it for improving edge detection, so to basically filter out the noise and just focusing on the salient parts of the scene. We have used it for document correction to get rid of the background, and we've even used it for low-level and task-specific saliency to find text in natural images. And then here a small example where we've actually used it for scene carving that actually is, or for retargeting. The original seam carving algorithm was published by Avidan and Shamir, and by using this saliency metric, we can make sure that the main object is not really touched, as you can see on the right-hand side of those two examples. So salient region detection, the method I just presented to you was very simple. So salient region detection is still a very active research field. A newer method used deep learning and much more complex, using orientation and size. However, our simple method is still amazingly effective. So saliency is also not just a low-level vision phenomenon anymore. It goes beyond texture cues such as orientation, size, and movement, and also includes object size and appearance, i.e. mid-level saliency cues. There has been a lot of research done in the last decade on this topic, using these deep learning techniques as last and classic before. So I'm just showing you one of our recent ones as a placeholder, but there are many more on other excellent works. So, and saliency also has a very personal component that has to do with emotions and experiences. And these high-level saliency concepts go beyond just a visual experience, and explore this direction could be a very interesting and fruitful in the future for many research topics. We haven't solved it yet, but we are still working on the topic. So let me give you another example where we've used opponency, and that is in our Superpixel and Supervoxel algorithms. What are superpixels? Well, superpixels are pixel clusters of an over-segmented image. They coarsen the image representation and reduce complexity by pooling the image statistics within meaningful regions. They're very convenient primitives for other algorithms to build upon and they have applications in depth estimation, body pose modeling, image segmentation, tracking, etc., etc., etc. There are several methods to calculate them. At the bottom right, you see one of ours called SLIC. And SLIC stands for Simple Linear Iterative Clustering, where we apply k-mean in 3 to 60 space of color values and spatial coordinates. We normalize color and spatial distances using maximum distances within a cluster. The spatial proximity term is the Euclidean distance, and the color proximity term is again the delta E term introduced before. The number of clusters is equal to the number of superpixels we get. There's also SNIC, which is simple linear non-iterative clustering, which was a newer version I'll introduce in just a minute. So here are some example results. where you can see what varies when you, yeah, exactly, when we vary the number of superpixels. So it's a good illustration of having lots of it on the top and fewer of it at the bottom. And here is a illustration. And here is another illustration of a newer version of our superpixels called adaptals. Part of the thing is if you are using superpixels, very often depending on the image content and the frequencies in the image, you either have too many or too few. In other words, if you have lots of them, like on the left-hand side, you're actually over-segmenting or really over-segmenting areas like the background, where you basically have no high frequencies and no changes. But you might be, if you take a coarser representation, you might be under-segmenting some of the details like the dots in the dress. So we came up with this algorithm called the adaptals, which just basically varies the size of the superpixel depending on the local complexity. And here I'm going to let you watch the video, how this is actually, this grows from one seed, and depending, again, using the exact same distance metric, once you actually go above a threshold of a difference, you're basically stopping. And this is how it grows. Now, I don't want to talk too much about this because in the interest of time, but you have the references to this paper on the slides, but then also, of course, on our website. Maybe just because it's so beautiful, here is another example. Again, we're starting with a local seed and then basically stop the propagation of the superpixel when we are beyond a given threshold, given, of course, by the distance metric. So what can one do with all these superpixels, supervoxels, adaptals? You know, as mentioned before, they are really a good pre-processing step for a number of applications, such as segmentation, tracking, depth estimation, body pose estimation, what you want. Here are just some examples. First one is a graph-based segmentation. The other one is also applicable now in medical imaging, mitochondria detection. And we have actually used supervoxels to estimate beauty ratings of videos. But, you know, there are many other applications that we did not think of. But the one thing is that we can say is that even today, when deep learning has changed the paradigm of many image processing and computer vision algorithms, superpixels and supervoxels are still very actively used. Here's a list of imaging domains that our first superpixel algorithm, SLIC, was used in. It shows the citation count per field according to Scopus. Besides computer science, remote sensing, and medicine, there are actually a surprising number of citations in mathematics. And under the category Other, you will find fields like economics and social sciences. So again, all this goes back to Euclidean distance and color opponency. Now I could actually, at this point, I wanted to talk about our work extending opponency into the near infrared. But then I actually realized that I would run out of time because I do want to show you how to use opponency and machine learning and present to you some of our newest research. I do put opponents in quotes here because it has actually nothing to do with color opponency, but much more to do with its dependence on decorrelation or disentanglement in machine learning jargon. So this work was published last year at CVPR, and one thing we have to thank all these virtual conferences for is that we do have videos. So So I could have talked about the video, but I missed a little bit my cue. But what you can see here is that we have localized edits. At that point in time, it was a new paper that showed localized edits where basically we can separate the local semantics in an image. So what do we have? We have two synthetic outputs of a GAN trained in this case on the flicker phase datasets. We show in the paper that deep generative models like the PG-GAN, StyleGAN, and the recent StyleGAN 2 learn a representation of objects, an object's part that is disentangled in the sense that various semantic parts, for example, the mouth of a person or the wheels of a car, have a significant ability to vary independently of the rest of the scene. Based on this observation, we propose an algorithm that performs spatially localized semantic editing on the outputs of these GANs. We were actually inspired by our previous work on matrix factorization for CNNs. Ido, in a previous work, developed a method to extract semantic object and object parts from deep convolution layers of pre-trained networks, such as VGG and ResNet trained on ImageNet. Given a few images as input, here we take 3, we take the feature maps A from a deep layer and stack them in a matrix on which we perform non-negative matrix factorization, resulting in a U and a V matrix with K dimensions. We choose which rank K. The matrix is then reshaped to a tensor, producing K sets of heat maps. These heat maps show good overlap with semantic objects and objects part. Here you see the results for K equal 1 to 4. In K equal 1, the body of the gymnast and the elephant are very well localized. Now keep in mind that these are images that the network has not seen during training. So we just feed them in afterwards, right? So it was pre-trained on VGG19 on the ICOSEC images. These are not images of the ICOSEC database. So, but you know, with K equal 1, the body of the gymnast and the elephants, they really are quite well localized. With K equal 2, the limbs form a separate cluster from the body. So here in red are the limbs and the body is in blue. With K equal 3, arms and legs are separated. And with K equals 4, the bar is also recognized. Similarly with the elephant example. Now keep in mind, as I said, the network has never seen these images before. Similarly, for another trained network and data set, so here is Resizing 50 on the Oxford and the Paris building images. So we could show that our method, which we, by the way, call deep feature factorization, outperforms the state of the art in both image retrieval and localization of the region of interest within the set of retrieved images. That later paper was then actually published at EUSIPCO. So we can similarly analyze the layers of GAN generator networks. Instead of non-negative matrix factorization, in this case here, we use spherical k-means. So we test multiple layers and multiple k. Here, let me show you a layer 32 by 32 with k equal 2. So you can see that it separates quite well the face and the background. So with k equal 3, we can already separate mouth and eyes. And then k equal 10, we get quite a good separation of all the facial features we're interested in. Whereas with k equal 25, we're just over-segmenting. Then similar to the 128 and 128 layer, here we're also using k equal 25, which is an over-segmentation. So we found that lower layers have greater control of shape and higher layers of texture. At an intermediate resolution layer, the 32 by 32 I showed you, faces are spatially disentangled into semantic objects. We label the clusters manually. This is done once, only once, offline per GAN and dataset. So using a large batch of generated images, around 200, we qualitatively evaluate the cluster masks at different layers and rank Ks and choose the most, whatever we call, semantic setting. And then we go and find the best overlapping channel for these clusters. Here is the channel for eyes, nose, and mouth. And then by manipulating these channels, we can make the local change to the semantics, i.e. we can change the look of a person as shown in the video. So now the video one more time. As you can see, the target, the eyes, then the nose, and then the mouth. But we're not limited to faces. Our method naturally extends actually to unaligned reference and target images. In this case, you can see how the bed, the pillow, and the window changes, even though they are not aligned. And here for cats, similarly for the eyes, the snout, and the bodies of the cat. So that was 2020, more or less a year ago. Now, of course, we are already much further. This area, as you all know, goes so far. And here, let me just show you some work in progress by Izan Pazhuzhskar, a first-year PhD student, or almost second-year PhD student now in the lab. So we are now actually able to take a single GAN created output and manipulate certain facial features without having to interpolate between two faces. So the one in the middle, the red with the red bar, you see actually the output of the GAN. And then you see on the top, using StyleGAN and the same flicker face, how we change the nose, different kind of database, the mouth, then the car style, and the horse color. These are all StyleGAN 2 examples. And here you have StyleGAN 1, big GAN 256, big GAN 256 for the dog again, for the sky, the bed, and the eyebrows. Again, this is now just taking GAN output and then manipulating, finding the good directions on what to change given the semantic meaning. And again, as I said, what a difference a year makes. So this is work in progress, hopefully to be published soon. So let me get to the conclusions. The concept of opponency, or if you will, contrast, dissimilarity, decorrelation, disentanglement, has played a central part in our research. So this idea of, what fits together, what doesn't fit together, partly inspired by the human vision system, but also partly just inspired by the simplicity of the concept. Now, as I just mentioned, it is present in the human vision system, and we can exploit it in numerous ways and improve visual computing in up and including the latest tricks of the trade, namely deep learning. So the results are presented here by primarily the excellent work of Radhakrishna Shanta, Edo Collins, and Izan Pazhuzhskar. However, I really want to take the opportunity to thank all former and present IBRL members who also contributed. Research is a teamwork, and it is the exchanging of ideas that bring individuals forward. Thank you.